that. Yeah. And why don't you take away? And maybe like before you start presenting, can you tell us a little bit about your background and research interests and so on, as far as you would like to? Yeah, I'm very curious. Like, what is your trajectory, and what made you think about these problems and so on?
Yeah, so I share with you guys that I'm a mathy person, engineering and math as an undergrad. And, at some point discovered that you could actually take investigations of especially computations, which pushed me towards doing master's degree in PhD gathering. That was one class. French, obviously. And everything happened. It's very hard to get in front of a person.
Actually, it's not my laptop, so there's a mic somewhere. I don't know where. But it's supposed to pick all our voices. I don't know. Is it hard to hear me as well, or is it
No, it's very easy to hear you, but we can't hear Anne at all.
okay? What about now? If I speak from here, can you hear me now?
Yep.
Oh, wow. Maybe it's just sorry.
That's why you see I'm opera singer.
You empirically demonstrated that. Loud.
Okay, can you hear me now?
Yeah, that's better.
Okay, great. Well, just unmute and stop me if I drop things. Okay, yeah, so PhD in France, and then I came to the US to do my postdoc, and then I came here to be faculty. I am very interested in human learning and what makes us flexible, which means that I study learning, but also how executive function contributes to all that, mostly from an experiment and computational modeling point of view, with some neuroscience.
So you said you started from math and then switched. Was that difficult, that transition?
I mean, some aspects of it, yeah. Yeah, I mean, I still feel to this day, haven't taken shit off on, right? Because
Yeah.
like I've definitely been like, oh, everyone knows about this, and I don't, but
Have to make psychology more mathematical somehow. That's the solution.
um, but certainly a good technical and mathematical training as well.
For sure. Yeah, advice for the undergrads around here. Okay, all right, let's go. Thanks for the introduction. Yeah, let's hear about.
Okay, so this is the flashy title. Not everything is around. The slightly less flashy title is that I want to understand human reinforcement learning, and I want to uh, deconstruct it in the sense of try to understand what its core components actually are, what the computations that support it in human here are. And what I hope to show you today is that it's less trivial than it sounds, one, and two, it's maybe more important than it sounds in ways of psychology, neuroscience, and potential downstream implications for AI. Okay, so just as an introduction, like humans are really, really uniquely flexible with other biological species, but also into this day still compared to artificial agents. We are very good at just being dumped into a new situation. For example, have a brand new phone, or during COVID, we all had to all of a sudden adapt to online conferences, and we're just make mistakes and then we figure it out, right? But we are very good at making good use of what we've learned so far to adapt flexibly. So really, intelligent behavior as humans as a benchmark necessitates this type of really fast and flexible learning. And humans are the only example we know that does that to that degree. They provide, for that reason, unique examples of flexible behavior complete with bugs. And we think essentially that the reason we're so flexible is that we take shortcuts and that work most of the times, but occasionally, fail. And that's very interesting because that reveals to us what those shortcuts are that allow us to be efficient. Right. So, for example, you might be very used to waking up at 6 a.m. and you might be dismayed when that happens when you're in the kitchen on a beautiful island that you can't just get out of that habit that makes you efficient. Most of the days. Okay, so I study this question from the point of view of reinforcement learning. And one thing I would like you guys to take away from this talk is that reinforcement learning is a really big word with many different meanings, and that there's lots of opportunities to go past each other. And so we need to be very careful about that. So in the context of cognition, reinforcement learning can be thought of as anything that allows us to learn by using feedback that is of a type, maybe more punishment, like something scalar, that has some value. Of course, I think here we all know about the computational side. There's a whole class of environments and algorithms that collectively are thought of as the reinforcement learning framework. And then there's neuroscience. And neuroscience, there's the network in the brain that, as we saw last talk, that is really solidly established as doing something that looks like reinforcement with local core to that, but as we last week, many other aspects of that are also established. Like, okay, so we have those three kind of nodes, and of course they're not disconnected. So we know, for example, that a good part of behavior is supported by that network in the brain, and also we know that there's a sub part of those class of computations that explain well the behavior. Okay, so and for that reason, often we merge that. So it's that one thing, and I'll try to show you today that I think that's great. Okay, so what's my agenda going to be? I'm going to try to deconstruct RL, and I'll start very, very quickly with an issue with human RL that the literature runs into, and that will be the equation for what I'm doing parts 2 and part 3 that try to go with like identifying processes. Okay, and before I start with the details of the issue, I'd like to show you kind of the archetype of experiments that we do to try to understand human RL. And by the way, I'm happy to answer any questions.
Actually, since you mentioned that RL has many different definitions in different fields, what is your definition going forward?
I try to not have one definition of RL. I try to be explicit about which part of it I'm talking about. And for this talk, it's typically the human behavior of learning
From reward or punishment.
Yeah.
It has to be explicitly, there has to be some feedback signal.
With some feedback signal. Yeah. And I'm happy to make that definition less flexible, but it's a good step. Personalization. Yeah, so I'm talking about the problem. Yeah. And can I let you monitor the chat in case
Oh yeah, sure.
questions? Yeah. Okay. Okay, so a human experiment is typically quite simplistic. We show participants stimuli screen. You can see this as a stimulus. And we let them make choices. For example, they'll have 3 kids in class. Really literally 3 kids and people. Sometimes we visualize it, much. People make a choice, for example, they press the third button, and then people get some kind of feedback, and that takes various forms, but typically states, for example, they pick the right action for stimulus, they go 0 points. If on the next trial they get stimulus again, what reinforcement learning tells us is that really they should not pick this one again, they should have between those two. If they select between those two, this one, with their chance of reward, right? They get reward in this case. So they should learn policy to apply this as button. It's quite simple at the trial level. And what we typically do is that, we vary the complexity or the, function or of various aspects of this. We have a different stimulus, like this stimulus here, that has a different association, such that if you pick button stimulus, you get the make sense? Okay, so that maps on fairly simply to the reinforcement learning framework, theoretical framework that says that you have a state, you have some kind of reinforcement learning algorithm, right, upon the choice, that you get some outcome from the environment, which trains this here. And the simplest one we start from, typically for cognitive behavioral experiments, is this one, the delta role algorithm. Is a simplification of the algorithm when there's no subsequent states. Okay, so that works really well. We like reinforcement learning in science community because it has really good properties. So this algorithm works well at the algorithmic level to describe behavior, but it can arguably be put off as a functional level model because it has an optimal kind of interpretation. This getting to the optimal policy under certain rates. And the thing has also an interpretation level kind of interpretation. And so that's kind of cool. Well, I forgot to say this is new stimulus is the state, the key presses of the and the other. So really, RL has become kind of a child story of cognitive neuroscience to the point that once I saw an NIH funding announcement that said that was all for like visual modeling of cognition, like perfect for me. And then like the last bullet point was like, if you're doing RL, don't bother, all is solved. I was like, so yeah, fear of misunderstanding there. But it is still remarkable, unique in its success. And I this paper, if you want to see more about this, reinforcement learning with more child for the 3 levels of scientific theory is reinforcement learning. People are defending that point, so I don't have to go. Okay, so that's great. And let's make that even more explicit. We are going to look at behavior or cognition of Micro's bubble. Say, okay, we have RL as reward-based learning. We can see in experiments and behaviors. We have a process level and we have the 3rd level of implementation here that is going to say something like corticostriatal loops with dopamine input are going to implement this. And we have those, 3 types of descriptions of reinforcement learning, and hopefully they match each other. And that's kind of my question today is like, well, it's great that RL works at 3 different levels, but is there actually 1 to 3 levels in such a way that this is interpretable usefully? Oh, and I missed the patience, so forget about this for a second. Or I guess I can preview it. And so the issue we observed is that actually it does not seem like there is this level of generalizability. And a very simple thing we can do to check I think the minimum requirement, if there is this correspondence, is that it shouldn't matter which RL task you take. Like if you take, task A and task B, and they're both reinforcement learning tasks, and you model RL, and you look at whatever effect of this task you want, like differences or which brain it activates or something like that, you should get the same base. And so my previous grad student, Maria, looked at that, and she's now at DeFi doing research. And we just tested whether findings in an experiment generalized to another one. And we did that in developmental samples. So the target here was like, if there's an effect of age on something in one task, is there also an effect of age on something in the other task? Or precisely at the individual participant level, does this participant's learning rate predict the same participant's learning rate even? So we had 3 different tasks.
Hey, sorry, you're cutting out again.
Okay, can you hear me now?
Yeah.
Okay, thanks for interrupting. Okay, so we had 3 tasks. No need details. They're all 3 reinforcement learning tasks, fairly uncontroversial. And we modeled them with reinforcement learning, the best possible reinforcement learning model fine, to capture those participants' behaviors, and we fit those models to participants' individual patterns of behavior. And then we say, like, okay, how does it compare across tasks? And long story short, it's pretty bad. So for example, this is here the learning rate for processing outcomes in 3 different tasks, average over the group and binned groups. And what you see is that just the absolute values are just completely different in the 3 tasks. 1. And 2, if you z-score tasks, so if you try to, instead of looking at absolute value, look at relative value across participants, that's the right plot here. You see that sometimes it looks better, like here there's a big, increasing effect of age on learning rate, but you see that it's not that robust. But for some parameters, like the negative learning rate here, it's actually anti-correlated. So yeah, no, pretty bad. And you can do that more formally by trying to train machine learning models to predict parameters from one task to the other one. And it works a little bit with some parameters. So, I'm sorry, this cut off. But for example, this left set of bars here is the noise parameter, and that's slightly predictable. But if you look at this one, for example, that's the positive learning rate. It's just not predictable.
These are observed behaviors or computational models?
This is all real data, like real participant data. Okay, so this is really showing, remember, something that we had observed in the literature is that paper 1 says there's an effect with the oral task, and paper 2 say no, actually there isn't. And there's lots of confusion about why that is happening and why we don't have this generalizability. And the case I want to make is that it is because the error framework is essentially too flexible and capturing too many things into its umbrella. And so that if we want to understand human reinforcement learning, we need to actually deconstruct it into its core processes that are more interpretable, each of them. Okay, so that's where I'll start. In part 2, I'll show that not everything is error, that you also need other things like memory processes to actually explain even the very simplest possible form of human reinforcement learning. This is not about advanced behavior. This is about just being always happening. And in part 3, I'll show that I'm actually not sure. Okay, so let's motivate the second part. And to do that, let's do a quick exercise of considering this type of task where you're choosing between 2 items. For example, the apple, the banana. You might, for example, choose the apple, and it might be delicious, and that might make you more likely to pick that. That's reinforcement. But if you think about any individual making that choice, you can think of many ways in which you might be, right? You might rely on what we think of reinforcement learning. Essentially, you might have built a cached value that you like apples 0.7 and you like bananas 0.5, and so it's apple. And that's what we'll think of value-based. But you might also have just been told by someone else that, oh, the apples are good today and bananas are kind of not good. And you might just have this information in mind and make a choice based on that. Right? So that will be a choice guided by short-term memory rather than value. Or you might remember last year when you went to your mom's orchard and picked an apple fresh off the tree, and it was so good, and you will take that memory, and that's what's going to be your decision through memory. And I'm listing those three, but really, I think that's the other ways. If you do some kind of reasoning, Mom went to that store today, and that store I know has good apples too, or any, again, not exhaustive. Okay? Yeah.
Could this be can you just squeeze all of the others into value learning by just assigning some sort of ad hoc value?
Yeah. So I think you can. It's just not going to match the neural RL side. It's not going to match that value part. So certainly there's definition questions, but if I'm trying to have interpretability domain of mapping across levels of representation, such that if I find individual differences there, I can tell it's coming from this type of neural process. So that type, then I can do that.
Yeah. I mean, I totally agree. There's value in teasing apart these. I'm just saying, like, if somebody is just like really likes RL, they can try to do that if they're.
Yeah, they could. Yeah.
Okay.
Yeah.
Can I follow up on that for a second? Yeah, it seems like there's two different things here, right? Like the value learning is like a process of learning, and these other things are like, how is the choice made at the moment, which is sort of happening separately from any learning process that might have happened in the background that could have happened by different mechanisms.
Yeah, for sure. So I'm using value learning as a shorthand here for the like the process that's in the brain that is using those cached glutamatergic brain network that is, we think integrating parts over time and building a policy that way. Yeah.
Okay, so I guess I'm asking, in all of these cases, you're acting on the basis of some estimated value for the two things. It's just that you arrived at that estimate by different means.
Yeah.
You could have arrived at it by RL, you could have arrived at it by being told, and so on.
Yeah, for sure. So here, so far, I'm just talking about value, and I agree. That's the examples I gave. I think all of this could be extended to, making choices not based on value, although, there's always a way to like everything into value to some degree. So the debate to be had there. I don't think it's necessary though.
Okay.
Yeah. Thank you. You had a question too?
Oh, yeah. I was asking, like, you're saying it's going to be difficult to kind of encapsulate all these into like a single state for a more coherent process. You need some temporal aspect that would help determine your future actions. Or assigning value to the current state.
Yeah, exactly. So you need to do like an online process to do but more flexible. Okay, so the point here is that it's about value, orthogonal to the point that I'm trying to make, which is that these are separable, identifiable processes that can be used independently or identified independently in the brain that all can contribute to learning behavior and choice behavior, and so even such a simple choice, is can depend on that, then likely it does in those learning experiments. And so we want to see if we can pull those apart and if it helps clean up that ambiguity we see elsewhere. So something I did a while back is try to do that with the concept of working memory versus more reinforcement learning. And to do that, essentially, we try to design experiments that pull apart some of the predictions from those two systems. So this type of process here is characterized by being sensitive to the effect of cognitive rewards over time, and should be paying attention to positive and negative outcomes, and breaking them into an estimated value. By contrast, if we think working memory contributes to learning, then we should see characteristics of the working memory process as it is studied outside of learning, which is very big sensitivity to load of the amount of information you try to learn, and also sensitive to short time. So it's sensitive to how far back in the past the information you're trying to hold in mind. And this picture just to show that evidence was are different. Okay, so it looks like that. If you're trying to essentially predictions out of this process, this one says you should be more likely to be correct the more rewards you've had for a specific a choice in the past. And we are modeling this with a very simple, what else I have over here? For the working memory part, it looks like this. It says essentially we should be most likely to make correct choices if the load is under working memory capacity, and then when it gets above our working capacity, then we should be our ability to use that information should be decreasing curve kind of way. You can put all this in equations. I haven't here, but that uses a couple parameters here. That's like how much do you use working memory and what the capacity is. And there's also a forgetting parameter that captures this effect. Okay, so we model working memory as like it's going to store information perfectly, like immediately, but then it's going to quickly forget, and it's going to contribute to the policy in proportion to how many items you can hold based on your capacity. Okay, so the model is going to be a mixture of those two components. And the way we're going to test it is with a very simple task. That's a bit like the one I showed you at the beginning, where participants see a stimulus on the screen. Bicycle, make one of three choices. For example, here, action 1. They get feedback. Here, that's correct. And then it's stimulus, action, feedback. Okay, so very simple. It's even simpler than you think because the feedback is deterministic. So for the bicycle, if you pick action 1 and it's correct, it's always going to be correct, and everything else is always correct. So with perfect memory, essentially, you just need to try 3 actions and then make sense. Yeah. So the key manipulation is that this is going to be one block, and you're going to see randomly interleaved the bike and the car, maybe 12 iterations each, randomly interleaved. So you have a short for trials block. Okay? And then the next block is going to be a completely new set of stimuli. You'll learn something else. And we just manipulate that size, set that you're learning about. So this one, for example, set 3, another one, 5 things, another 2 things, up to 6 things. So it's a pretty simple manipulation, but it's getting directly working memory. Both the load, also the forgetting aspect of working memory, because of course, if you have 5 stimuli, on average, you see them every 5 trials. There's variability around that. You can pull that apart from the load effect.
So when you say working memory, are you saying that the system need to store state, action, and result?
Yeah, so I'm not saying they need to, but I'm saying that they do.
I see.
Yeah.
And then you said that they only need 3 trials to do it correctly. But I think that's actually reasoning, not like learning the task in a reinforcement learning way, because with reinforcement learning, even if you have perfect memory, you're still updating it incrementally, right?
Yeah.
But I feel like you're trying to say something different, which is like using a perfect memory to reason out which one is the correct choice. But that's different from incremental learning.
Yeah, I'm not it's not incremental, and I'm talking about behavior.
Yeah.
I'm talking about the fact that in the end, this is a learning task.
Yeah.
Participant's job is to get it right.
Yeah.
And if they're getting it right, they've learned it. And whether or not it's depending on URL or working memory or something else, Again, if working memory is doing all the job in this learning task, well, that's what it is. Does that make sense?
Yeah, yeah.
It is an important point. If you don't on board with that, but it is a huge point of our debate. Often, what are you talking about? Working memory is not a learning process. I'm like, sure, it's not a learning process. That said, it contributed a lot to learning policies, and we need to acknowledge it, although we're missing all the variances. Okay, so predictions from pure reinforcement learning model look like this. So here I'm plotting accuracy, a learning curve, right? Accuracy, and this isn't time, this is iteration, iteration per stimulus. So it's how many times have you had a chance to see the bicycle. So this is iteration 1 for the bike and iteration 2 for the bike. Okay, and the key point here is that if you take your kind of vanilla reinforcement learning model, it just predicts no effect of set size. And that's just because it's accumulating the hash value of each action and stimulus independently of each other. And so it just really doesn't care whatsoever all the things that are to be. So obviously, you can like big this around and make it a bit more sensitive to set size. For example, you can add pairing to this, and then you'll have a but it's not its core prediction. And it's very clear that it's not a good prediction, but I'll show you the data to support that. So this is participants. I think this one is, I've done at this point, I don't know which one, but it's very, very robust finding, and I think this one is 80 participants. What you want to see here is that learning stimulus action associations, the blue curve, it looks perfect, right? Iteration 1, iteration 2, iteration 3, and then you're actually not at 1, but you're at asymptote. That's normal. A random curve. So that looks like perfect memory. Well, effect, but there's a very clear effect would. And essentially, the more things you're learning in parallel, the more total it gets. Everything converges to a high asymptote, which means it can't just be working. It's just working memory. You would never be because no one has capacity. Okay, but if we take our hybrid model here, that's both working memory and we capture that pretty well. We get a good match to the behavior. I can all the formal person and etc. and do that. It's years now, but really, what we found over the years is that you just can't capture this behavior well with a single process. No matter, there's always one reviewer who's testing their way of just, I want to unify model, please add this to URL, and I try it and it never works. So really, I think it's very strong that, need to processes to explain this behavior. I think it's also intuitive, right? I mean, if you're thinking about doing this task, like, of course, you're going to this figure forward as equal. You're just going to follow that in mind, and over time, it's going to we're going to have to think about it anymore, and probably that's around taking over. But it matches, I think, most people's. Yeah.
Do you think they're in parallel, or there's some arbitration like at a higher level to decide which system?
Yeah, that's a great question. I didn't put any of this in my slides, but we have papers on that. I think there's multiple ways in which processes are less independent. I'm making sound here. One of which might be, so in this model, for example, the mixture weight is fixed. And I think it's very likely that that's not, that, the mixture weight probably, sounds high with working and uses over time, for example. And actually the original paper on this had this type of mechanism, essentially to say, the model that's most predictive of outcomes should become more responsible. behavior of the time. We we haven't been doing that lately, partly because I think that happens over a longer time period than we observe here, and the model. So that's one way interaction, but I think there are more subtle and more interesting interactions too. For example, we have very good evidence that using working memory blocks RL some degree. The thing that well, anyway, I could talk more about that later if you want. But really kind of important downstream effects.
Kind of
Sorry,
related.
did you say that it blocks RL?
Yes. Yeah.
Okay. Is there something to read about that?
Yeah. I have I think 4 papers I could.
Okay. Thank you.
The long and short of it, the way we observe it is that, as you see here, people learn so much more efficiently in size 2 than in 6, for example. Right? And so you might say oh, great, we should all be learning things like under low load, right? But then what we've been doing is adding, after the whole experiment is concluded, we distract people for a little bit, and then we give them a test phase where we tell them hey, you're going to be tested on everything you learned, including, the thing you learned 15 minutes ago, like action to press for the bicycle. And we're not giving you any feedback. So you can't learn anything, you can't use working memory anymore because it's back in time. And what we find very robustly again is that people forget much more what they learned under load than what they learned under high load. So their performance is much weaker in the test phase for size 2 than size 6. So what they've learned easily is just not weak.
Cool.
So that's it's kind of cool, I agree. So and to me that's also a great example of whoa, that's not your issue, it's dangerous.
So this the plot, your model is reproducing data really well, and I'm wondering, have you tried ablating just RL or just working memory, and how does that look? How bad the prediction becomes?
Yeah, so if you apply just working memory, you get back to what I had here.
Oh yeah.
Right. If you get just working memory, you get something that looks like this, except it asymptotes right here, right? Because essentially we fit people with roughly capacity 3 or 4 average, which matches computations, and that means that in size 6, it's holding only about half of the information in mind, so it can never ever reach a good policy. And that's kind of an important one too, because I often get the criticism that, well, don't you just call working memory or algorithm? I mean, I could, but it's a really bad one, right? It can never learn a good policy, right? So in that sense, to me, a low bar for something in neural algorithm is that should be some kind of guarantee that it can learn a good policy, and it just can't.
I think there is one more question. Let me see if I can read that. I can only read the captions right now, so I don't have the perfect context, but is it possible that RL is happening at a longer time scale, and that is how the mixed value memory process is created for the short run?
Yeah, so I mean, RL is definitely happening slower. You can see it here. If it wasn't there, if the question is whether it's even slower than what we're seeing here, I think that's not impossible. I think that then we have to explain what is this process that is happening, and maybe we can get back to that after my third part, because I think there's kind of questions around that there. Okay, so I just want to spend one slide saying why I think it's important to do that. I'll give you the example of a developmental study we did with 300 participants, where we had participants 8 to 30 years old doing this task. There was just up to set size 5 in this case because we wanted to make it short enough for the 8-year-olds to be willing to participate. And as you see, every group shows the right pattern of behavior. Well, the best fit model is the same for all groups. But what's less visible this is that there's a very strong effect of age. So if you plot dot here as an individual participant, you can see that there's like accuracy overall increases strongly with age. And if you plot the effect of set size here as a function of age, it also decreases with age. So like this is tighter. That makes sense? Okay. But what we can't know just from this data is like what is driving this difference in accuracy? And we did an interesting thought experiment around this. So, well, let's imagine we hadn't done this set size manipulation and instead done separate experiments. So, for example, maybe one lab had an RL experiment with 3 stimuli. What conclusion would they have drawn? So we can just take the set size 3 data of those participants and fit it with an RL model and see what we conclude. So, for example, that's what this is, and you find what you conclude is, oh, the reasons the kids are worse than the teenagers is that their behavior is more noisy, off max. And so we have an effect of noise, we have no effect of age. So that's our conclusion. We published our paper. We say like kids, less and less noisy over time. Okay? And then this other lab did the same experiment, but chose to have 5 stimuli instead. So let's take the subset of 5 data that's asset 5 and fit the same RL model to it. And this is what we get. We get absolutely no effect of noise here. It's flat with age. Instead, we get a super reliable effect of age on the learning rate. Okay, so if you try to capture just the average, the behavior in each set size, you're not thinking of it as coming from 2 different processes jointly, then you're drawing wrong conclusions. The RL model fits the data very well. It's summarizing the behavior quite well. It's just assigning the variance in the wrong place. So if we fit our model to this instead, what we get is this. I don't show you all the parameters, just for simplicity. But what we find is that the strongest effect is actually this learning rate effect, that the improvement in behavior age here is driven really mostly by changes in learning rate, no changes in working capacity, for example, that's very stable the ages. And the reason we're seeing different things in the 2 experiments is that putting processes to different degrees in there. And that's what I'm plotting here. That's the relative contribution of the working the RL process and working memory contributes less and less with higher set sizes. And because if you're slicing here versus here, your variance contributes differently. And
Is panel C just the mixture coefficient?
Yeah, that's right. Yeah.
That makes sense.
Makes sense. And so we think that that's a snapshot of what's happening in the broader literature. People have different RL tasks. They recruit different sub-processes to different degrees, and that leads to different conclusions. And the way out of that is to say, well, RL is too flexible. It's going to summarizing the data super well, but not in a way that maps interpretably to stable neurocognitive processes. And so if we want to get to a more generalizable knowledge in the field of reinforcement learning, we need to take into account those the validity of those cognitive processes and try to capture that. Okay, against you of that. So if we go back to our deconstruction here, we started from this, and what I'm going to say instead is so far is that actually we can't really explain human RL. It doesn't map all. Instead, we need to say, well, actually, there's other processes too. In this case, I've shown that working really captures a lot of the variance and that's problematic to a different brain. And we also have RL here that hopefully still maps on to the right brain. Okay, but now I'm going to make the story more complicated and tell you that actually this part is shaky. But any questions before that? Can you still hear me? Okay. Okay. So is this third part is going to like lead us into a debate before another it's very free. So let's go back to our conclusions so far. Fast and flexible human learning relies on the strong guidance from working memory. It is not a neural process as far as I'm concerned. And the reason I think it's not a neural process is that it can't converge to an optimal policy under most circumstances. Okay? Obviously, that's going to be a definition kind of issue. So, but I don't think most people would be happy calling that a neural process. And then we had value-based NRL showing the leftover variance, important variance, right? Like and meaningful. We see that it captures individual differences in some important way here. So we're hoping that that maps onto the circuit, but we want to make sure. And one reason I started having doubts is that I observed something really weird in this task that I told you. Going back through this task, and we're going to dive just a little bit into the RL process. This equation here, we're tracking the value of a choice using the questionnaire with the learning rate. Okay. And we have this learning rate. We have kind of like we discussed last time. This learning rate is actually importantly dependent on the sign of the reward prediction error. So we have these asymmetries. That's always part of the model. And we are going to define a bias term as the ratio between alpha minus and alpha plus. I think that was the optimism or something like that. It's really important that we have a non-zero or non-infinity kind of bias, right? Because especially in our task where you have just 1 and 0, you're not integrating outcomes, you have no way of getting anything that's correlated to the true expected value. Okay, so that's a very important. I was super puzzled when I realized multiple data sets here. Each the x-axis is a different data set. Each dot is a participant data set. Show a very big optimism bias. So alpha minus being very small. Oh, and this is the behavior across those tasks. You see it's very repeatable. And so I was wondering what was happening in RL here. Like, why was negative outcomes just consistently not really well included? I really think there's lots of information to be found in behavior before jumping into modeling. So I wanted to figure out whether this was some kind of artifact of my modeling or fitting procedure, or if I could find evidence in the behavior that people indeed did not pay attention to. So I'm going to walk you through my reasoning for doing that. So the idea, let's imagine we have this blue stimulus, okay? And those are the 3 actions you can make, and this one is a correct one. And because the feedback is deterministic, if you pick this, you get rewarded. Okay? So let's say the participant picked this action 3 times in the past and got rewarded 3 times, so we have 3 rewards here. And we have 2 possible errors, okay? The middle and the right one. And let's say people picked this one twice and this one once. Okay, so that's kind of like I burnt myself on the stove twice and I burnt myself on the kettle once. Okay, you know, the more you burn yourself on the stove, the more you should avoid the stove. Okay? And so the idea is that if you're going to be making an error here, well, you should be more likely to be making this one. you're doing reinforcement. Right? Like you're just learning, the more errors you make, the more you decrease your value, the less likely you are to. Okay, so that should be, for, I think, a signature of RL integrating into the outcomes. Okay, so what I'm going to do is I'm going to take only error trials, and I'm going to count how many times they've made the same error as they've chosen trial, the other error they've chosen. And I'm going to hope that this is lower. We're good with that? Okay. And this is stimulus dependent, right? This is for the stimulus. And those are the number of times. Okay, so if you do that, the y-axis is this count of past errors for the current stimulus. And you look at low set sizes, you get what you expect. People are good at avoiding errors they've made in low set sizes. Great, that's rational. But if you look at higher set sizes, the difference decreases and disappears in high set size. Okay, so sensitivity disappears. And my model that in 10 different papers, once I actually look at this specific aspect of the behavior, totally cannot capture this data. Okay, so this is the best fitting model for the 10 years. It just does not capture that. And that's logical, right? Because it has working memory, which pays attention to negative outcomes, so should be good at avoiding errors. And it has RL, which integrates negative outcomes, so should also be good at errors. Okay, so the dotted line here is the model, and it's just always going to have a gap. The way that. Okay, so that tells us there's something wrong, and that something wrong is most likely in the error part, because we're doing fine. The low load, we're working on it provides most of the parents, but when we're doing the high load, it's more contributions of a slower. Okay, so that's where we. And the only way to get this is to somehow counteract this difference, right? Like, you know, working memory says you should be more likely to avoid an error. You need some kind of process that tells you, no, actually, you should be more likely to repeat an error. And
just a clarification question about the experiment. So when you get the real data for high load, for example, does it happen after many, many trials where the participants have learned? Or do you have like, I don't know, just a time course of how this curve evolves as they are doing this task?
yeah, no, I do.
Maybe like early on, it's better matches the model. And
Yeah. Do I have it? Yeah, I'll show that to you in a few slides. I don't have it as a learning curve, but I have it as early and late. And, yeah, and that's the thing.
Sorry, when you say set sizes, that's the number of options?
That's right. Yeah.
And then on the y-axis in these plots, it's the
number of I'm counting how many times error has been made for the stimulus in the past.
okay.
Yeah. Sorry, the set size is not the number of options. The number of options is fixed at 3 all the time. The set size is the number of stimuli that you are learning about.
Okay. That's helpful. Thank you.
Yeah, sorry about that. Okay, so we need a process that counteracts actually that process that when you're making an error, you're more likely to make that error again, which is exactly what you're doing for outcome. So in the end, what we think is happening is that we have a learning process that's instead of saying you're going to be more likely to make a choice the more rewards you got, we're going to say you're going to be more likely to make a choice the more times you made this choice. So it's going to be outcome insensitive, to be sensitive to the number of past iterations, and it's not going to care about. So we're going to model this as the likelihood of repeating a choice for a given stimulus increases the number of times you choice. Okay? And you can actually model this as exactly like the RL equation, but you replace the reward. So it's going to count a relative frequency of the different actions, how they're associated. So it's very dumb. It's kind of like, you know, the more I do something, the more I do something. And that's remind you of like hidden or habit-like or much simpler essentially than with learning. Certainly not learning anything like value. Okay, I don't think anyone think of this as a neural process either. If you put this on its own, it's just going to keep things simple.
Can we try to interpret what H really means here?
Do you mind if I have some simulations to try to that later. So first I like to show you that it makes sense to look at this and then maybe. Okay, so now I still have the same mixture model. Key memory hasn't changed. This habit process, with yeah, same mixture process as before. And so when we do that, we still capture the learning curve really well, but now we also capture the error pattern quite well. And this is what you were asking about this. The black line is the early. You see that early on you have higher sensitivity to errors, but later on this curve gets negative, meaning that here. Sorry, I should say this is blue line is purple. And yeah, that purple curve gets higher. And so people really repeat more the error that they do. And the model captures that really well. Not just in, again, you can do the whole exercise of person and it's the same story. And you can check across all 6 data sets. You see that this pattern is extremely repeatable across 6 data sets, and the model wins. Okay, so implications, which is going to get back. Oh, and this is impress and come. So the implications is that so far in the reinforcement learning behavior, shown that memory guides a lot of this learning. Again, I agree, on learning process, but in a very important process to guide flexible behavior. And then we have a slower process that we thought was RL, but appears to be something kind of different that is really value-free, at least. And that does not track value, but tracks frequency. And to try to understand that process does, I did this simulation where I do a probabilistic experiment. So we have 2 options, A and B, that lead to reward 1 or 0 with probability. And I vary that continuously to see what policy there. So if you look at the top here, I'm putting I'm mixing working memory with RL, and I'm showing what that policy is, and you see essentially that the policy is, as you would expect, but quality of pick reaction A is going to be as a function of this expected value. And it's going to not depend much on how much working memory you use. Okay. Now, if you look instead of at this new model that has the H agent instead of RL, if you don't have any working memory, if the mixture weight here is 0, you see that this policy is random. Okay? And that's as it should be, right? It's not paying attention to reward, so it has no way of being sensitive to outcomes and to estimate actual expected value. So it is not a process on its own. Okay? But the cool thing is that as you mix it with memory, it does come to present RL-like. It does come to learn to pick action A, higher probability, the higher the value of A is. And that's because working memory essentially bootstraps into learning this policy. Working memories are often enough to tell you, oh, you should pick action A because it got rewarded, or you should avoid it because it got punished. Then that's going to be enough of a bias to drive that other process to learn, okay, I'm picking this more frequently, so I should pick. Does that make sense? And so that could explain why, for those past 12 years, I just confused that RL for this process, because unless you look at those errors, the pattern, they look the same. They look the same. And so you can't really put them. Okay, so but that leaves us a little bit in a pickle, because we we don't have RL anymore in our model here, right? Also, we don't really know what this H thing is, so I have speculation. It could be a much more Hebbian component that has been speculated in some models. It could be a habit loop value, and here I really want to shout out to this paper, including Amitai, who's a faculty here, who had like a very similar model in this paper, without the working memory component tested, but that had really a theoretical idea in this paper that showed very similar simulations. And I also want to say that I haven't shown you, but we find the same thing in a probabilistic learning task. It's a bit harder to interpret because it's harder to only factor out working. And for that reason, it's harder to add that. But we have, I think, strong solid evidence that still. Okay, so we started from this and we said, well, okay, this is out. And we definitely need to have working memory. But now we're here. We're like, okay, we have working memory, have this dumb algorithm, neither of which can reasonably called reinforcement learning algorithm because they really can't independently run a good policy. But jointly, they run really well. Like jointly, they run well both in low set sizes and high set sizes. They complement each other as well. Now we have speculation lands, but we have working memory that is well studied and maps onto the network. But for those two, I'm like, I'm not sure what to do about it because there is very strong evidence for this, right? And there's very strong evidence for this mattering. And so I'm just not completely sure at this point, like, my findings map into that, or really this one either. There's been, of course, really cool findings recently, speed paper showing also action prediction errors in the striatum, which we map very well onto this model too. So maybe something to be said there. Maybe, it's also known to some degree support memory, so maybe there too. But I think there's lots of questions to be asked down the line. And I also don't want to overstate my case. Because I didn't find RL doesn't mean RL. Certainly our error pattern contradicts RL predictions in this model. But again, it could maybe be a different frame, or it could be maybe that it's off for some reason, or that's recruited in this case. We are trying to experiment where we're trying hard to get all process. But still, it's striking that in this specific experiment, we just can't find it. Okay.
There's a question.
Yes.
Do you think the size of the reward, or whether it's real reward versus just a thumbs up on a screen, matters for which systems get engaged?
So for the second point, not at all. I think in humans, there's really lots of literature showing that symbolic rewards are just as good as non-symbolic rewards at eliciting learning and motivation and the same processes, etc., etc. So I think that's I feel quite confident on that one. For the first question, the amount of reward, I think that's possible, and that's actually the manipulation we're going after with Max to try to see if we have more variance in the value space, we can have a better chance of getting RL. So I think that's a possible explanation for finding it. That said, I'm interested in that's what's happening, actually, because we've done this experiment in the past with different value outcomes and found very, very minimal impact of getting 1 point or 10 points example on behavior. So yeah, we'll see. Yeah. It's more
Like, and the question was, sorry, the question was about the size of the matter, but it seems like you're saying probably not, but what might matter is how many different kinds of those like experience. Right?
Sorry, we couldn't hear any of that.
Oh,
speak louder, okay.
okay. It seemed like your question, I think Rosa, was more about does the magnitude of the reward matter or the size of the reward matter? But I'm trying to understand what Anne's response was, and it seems like within the same task, what matters more is how many different kinds of rewards you're experiencing, which makes it a bit harder potentially for working memory to remember what you just obtained because it's not either 0 or 1, but it's like 18 or 54 or 95.
Yeah, possibly. So what we have done in the past is have some blocks with 10 points and some blocks with 1 point, and that has next to no impact on the behavior. What we're doing now is what Guy is describing, meaning the stimulus is worth 1 point and this one is worth 2 point. And are you going to have this action is worth 1 point and this action is worth 10 points? And that's going to, let us see a bit more around size. I don't know. I think in the past, all those manipulations have been, in other tasks, have been confounded by the use of working memory to know the value difference. So we're trying hard to unconfound that and then see what's up.
Are these points proportional to dollar amounts?
No, but that doesn't matter, and
That
there's
doesn't-
good evidence.
Really?
There's good literature on that.
Wow, okay, interesting. I would have expected that to matter a lot.
It really doesn't.
Okay.
It really doesn't. Humans are motivated by. It fits though with the RL theory, right? Like that in the end, you just TD, right? Like symbolic things like merit value. Yeah.
It's just intuitively, if I'm a participant, I'm just like I'm running late. I'll just push buttons to just get out of here.
Yeah.
Instead of that, if it was like I can win $100, I'll pay attention now. So
Yeah. But if you're engaged in the task
yeah,
in the first place,
yeah,
you can't really fluctuate that much.
yeah.
And so that variance won't really. So certainly we have. I should clarify that whether you pay participants or not does help with compliance. Ask, but doesn't really help with when people. Julie?
Yeah, thank you for the great talk. It's really interesting. I was wondering when maybe RL might come into play particularly intensively, maybe is when you have a change of rules of like sudden surprise change of like what is rewarded, what is not rewarded anymore. And that working memory cannot working memory and habits together cannot really take the turn, right? Take that chat turn in terms of the change of rules or the unexpected new stimuli or something like that. So there are experiments where you are changing the rules in the middle of the thing or like introducing new stimuli that have never seen before. And I don't know how algorithmically we can see whether whether like RL would take over and better explain these particular shifts.
Yeah. So just a quick note is like they see new stimuli every 4 minutes here, right? Like each block is a new set of stimuli, so that's lots of novelty. It's the opposite actually. RL is at least this type of RL is just slow, right? And it's inflexible in the sense that when there's something new, you can learn before you can learn again, right? Like if you have like learned that action 1 is worth 1 stimulus and all of a sudden it's worth 0, you have to learn all this before you can learn the other one and start doing it. So it's really the opposite actually. We think that memory is essential when there's in the experiment, when there's reversals, when there's new things, and we think actually that working memory you know, to me, the AI implication is that working memory is actually going to give you the quick and dirty, you know, like let's get quickly, you know, be flexible and guide behavior. It might not be very optimal, but at least, you know, it will get us to sample the right types of things, and then we can, you know, build the more stuff with it.
So habits and reinforcement learning would be the slow system
Yeah,
behind the
absolutely.
scene. Okay. All
Yeah,
right.
yeah. Well, and I'm actively avoiding the implicit and, you know, explicit and stuff like that, because I think, you know, I don't have data to speak to that. And to me, it's very much an open question whether the RL learning process is how explicit that is, I guess. But yes, it's the slower.
Right. Yeah, it would be interesting to have if it exists like an experiment where you can like vary the policies and contingencies so that you can see what mechanisms are taking over the other one over time.
Yeah, so we do
That's
have
possible.
an experiment that is this experiment with reversals all the time, and we designed it so that we could isolate working memory actually, because we did that RL would be, you know, like useless in that situation where things change all the time, and that's what we find, you know, modeling. Yeah, so
Cool.
yeah, so we do have that experiment.
Very cool. Thank you.
Okay, I have like a bit of a conclusion and a few further thoughts that I think be of interest to this community. So first, I hope I'd like to convince you all to, you know, not just speak RL, but like clarify the words, like what type of RL you're talking about, because clearly we don't have good one-to-one mappings in them, and I think it does lead to huge amounts of confusion of the literature. I think, you know, the cognitive literature is ripe with like, oh, you know, people did this RL experiment and I modeled them with a reinforcement learning model, and they had a patients had a lower learning rate. So that has to mean that their dopaminergic system is messed up. And no, like too much mapping between that. But you really see this, and you really see this in like I'm not casting the stone on anyone. Like it's really, you know, we're like in many places, and you're just making too much reverse inference, and it's I think it's hurting the literature. So I think it's really important to be careful there. Um, we, you know, that paper to say that to some degree, that you know, there's lots of overlap, but also lots of differences, and so there's lots of opportunity for crosstalk, but we need to be careful around the wording. I'm not going to go through all of that. And then I just want to give you some further thoughts, because lots of other things with reinforcement learning, and some of them I think are relevant this community. And the one I'll give an example about is when you take this reinforcement learning framework, you have that logical reward function here, right? And again, I think when you're coming from the AI side of things, it has nothing magical to it, right? It's just like, oh, I want my agent to do this, so I'm going to define my reward function that way, and it's going to be fine. And when you're neuroscientist, maybe working with animals, we're going to obviously function is related to primary and rewards, and we know what that is, and it's easy to feed in. And we have a brain system dedicated to computing that. And I think talk say like essentially we're going to define reward as whatever activates dopamine, because that's the operational definition that leads to this reinforcement. Still great, let's do that. But then when you take humans, I think it's much less clear. And you humans, you know, have goals, and we're much more flexible in setting those goals. And I'm going to critique Gaia here for some of those slides, because essentially we know that we have a huge spectrum of things that motivate behavior. That goes from unconditioned, like food and drink, to conditioned in the TD sense, meaning things that we've learned it can be predictive of reward, like points or money or stuff like that. But we also do all kinds of things that don't reportedly to to any of this, right? Like we climb mountains or we art or we run marathons. That's very costly instead of being rewarding. People like go to great length to meet a specific goal. This curve, I love this curve. This is like the running times. You see that like if someone has a goal of running it under 4 hours, they're going to expend that extra energy to like actually make it under the 4 hour clock. It's so abstract, right? It's so like random, and nevertheless, it's really can be traded off for very real, energetic input, right? And and so we're taking those goals, we're deciding on them. We don't really know how, and Gaia again is working on that. And somehow it's fitting into our educational and learning system. And I think from the AI perspective, that's trivial. You just define your reward function as like getting hours. But from the neuroscience perspective, it's really trivial. Like, why would, like I be able to tell my dopamine neurons to fire if I'm at 8:59, 59 and not at 4, right? And so we really don't understand how we have that flexibility setting this reward in the brain in a very online, flexible way for completely new goals that just don't relate to real rewards. And so we're trying to understand where that reward comes from, and we think that this, but we think that this other processes contributed to that. And we are also thinking that every single part of this diagram here actually this important cognitive processes contributing to it. What is a state like, and how does knowing what a state is help us learn more flexibly? And we know that that matters actually same for choice. And so lots of food for thought there, and I do want to finish by thanking audience, my funding, my non-members. Yeah.
Thank you.
Yeah. We have further questions.
So does your framework or algorithm explain some of the fMRI studies?
So the difficulty there. So we did this experiment in Spanner and to get the practitioners on the other side. When I was alluding to this edition that working with reinforcement learning, the difficulty in applying this framework to other fMRIs and other reinforcement learning tasks is in the very flexibility of working memory. So we designed this task to be maximally insensitive to exactly what working memory is doing. And to be able to reveal movement of working memory no matter exactly how you do. And so you were saying before, like, well, what is working memory holding? It could be holding, stimulus action outcome, but it also could just be holding policy, for example, or it could actually be grouping things in a weird way, and it would still lead to better performance. Working memory tends to be studied from a very perceptual perspective, especially in the neuroscience field. But actually, there's a long history of working memory in psychology that emphasizes the fact that working memory is really a mental workspace. Like it's hold in mind self-generated information. You can transform it internally, and that's very important. And I think what happens often in all tasks is that people maybe do some kind of reasoning or inference or something like that and hold that in working memory. And we're picking up that a lot because it's fundamentally unobservable. And because people have so much flexibility to what they can do with working memory, it's very hard to parse that out of most tasks that do not explicitly manipulate, which is why we went through this very blunt manipulation of just because there it's that working memory matters, even if we're not sure exactly what it is.
Yeah, I'm just thinking that because you showed that at the behavior level, it behaves the same as RL algorithm. And when we think about all classical papers in RL, which taps into the striatal circuit and yeah, just the
I agree. I agree. It's difficult to figure out how to square it out, and it's difficult in large part because I can't really go back to those experiments and say like, okay, that was working memory. I have to be experiments that allow me to carefully parse out working memory and then ask what's happening there. Which is why, I'm like, there is literature saying dopamine, like plays an important role, for example, in deciding what to work out of working memory. So a hypothesis might be on some of that. I don't think it's quite high because working memory doesn't allow you to learning system, right? So then you have to have these effects in a way that's also consistent with the short-term effect of around. It's hard to see squared out. So I'm not sure, and no, I'm open to suggestions in the future, but yeah, that's why I don't want to overstate my case either. There's lots that are hard to square up with this, and so we choose to them.
I really like your point about how the literature could be a mess. I think the similar scenarios with predictive coding in vision, that everybody has their own different meaning, and it's just really hard to parse through what different people mean. And Eli seems to agree. So I guess, I want to ask you a question about, okay, you have this model that has a working memory component and habit. It's still not clear to me where's the feedback about the task success or failure come in there.
The working memory.
The working memory part.
Yeah,
the habit is just completely insensitive of any outcome. It's just basically, if you press this button, press it more.
Yeah. You know how sometimes there was this funny thing where I'm in a choir and the new conductor this semester, she learned everyone's names very quickly. I said Hannah and Heather, and she kept saying Heather for Hannah and Hannah for Heather, and like she was like, like, you don't go this each time she kept doing it. And I think we've all had that experience of like maybe people like who mess up left and right too, or like sometimes there's two things like I can never remember if it's this one or that one, and the more you're think about it, the harder sometimes it feels like. And I think it's a little bit that it's really this like, if you keep making a mistake, and you can't like train yourself intensively to avoid that mistake for a while, like it's very hard to get out of that. I think it's a little bit different.
I have an example for you. So I'm still struggling to understand month, day, year. So I always go like year, month, day, and then reorder to the American way.
Exactly. And the more you make the mistake, the harder it is to get out of it, right? And so what this says is like, essentially you need to put yourself in a situation where you make it correct enough times. No, but that won't work either, right? Because we say working memory blocks learning too, right? So it's very similar to space. Essentially, if you learn things too much in a row, then you'll get it right, but it will also block the habit learning. If you learn them too far apart, you're just going to keep making the mistake, and so you're going to reinforce the mistake. But if you do it just the right amount apart, then that you get it right, not wrong. So you have enough working memory to guide your choice, or other things. But not so much that it blocks your prediction, right? And so lets you have a training signal over your process. But again, I haven't done a critical file, right? So and I'm very, very, very of any of my findings because I feel like it's I'm not sure like that.
Yeah, well, that makes a lot of sense. So I guess if there are, what about other questions? Yeah.
You had a question, sorry,
I kind of have a question. So I really like your idea of that, we need to define the reward function with certain state action first. And I feel like even before that, we don't even know how to figure out the state space and
Yeah.
action space. And I'm curious about how you think about that and how should we study that in a systemic and rigorous way.
Yeah, yeah. Well, I mean, you might have noticed my lab tends to be very controlled experiment focused rather than realistic. Um, and the way we've been trying to do that is baby steps, really say like, okay, let's first show, you state space, the more complex of the choice space, a bit different. Let's just show first whether it impacts learning and in which way it impacts learning. And we've definitely seen that very, very quickly. For example, an experiment where, for example, manipulated how nameable, learning about a sheep and a cow and a chicken or three different sheeps that looked very, very visually discriminable. And see a huge impact on learning, and actually not just from the working memory size, but also from the parallel side. And so let's start from this type of place to say like, hey, let's assume, that wherever the experimenter gives you a state space is a state space and is not going to impact the algorithm. Actually, it is going to, and so we need to. So we're expanding on that after that, but we always go little step by little step. Same for the choice space. It's like, does it matter if you're just choosing the key, or does it matter if you're choosing, like if your choice is like box, red box, or green box? And as far as the function, if you're just doing model, like that's just 1, 2, 3, right? Like who cares, right? But actually, if you're participating in this experiment, it in a similar way by pulling some resources from you that then.
Yeah, I'm just thinking in the context that humans are so flexible and so good at generalizing what they learn to new task, and I feel like part of that is because we are very good at figuring out the important state, and like we can extract the important state among a vast space, and and I feel like that really.
Yeah, no, I completely agree, and there's sure attentional learning that does that. I think the other way in which we so flexible is that we can generalize findings, and so we've been working on that by saying like how we can learn a policy and then and then see how that can be applied to text. And you can put that in that framework, for example, by saying like actually the level of abstraction in your choice might be as high as selecting rule to pay attention to. Yeah, and so we think, this type of framework is that too, some evidence still there. I completely agree with you. There is existing work. And yeah.
Yeah, I was wondering if this is like purely like an emergent human property, or have you seen this sort of like habit formation in other species as well?
No, I think habits are actually easier to study. I alluded to that paper and sorry, I cited it, but it's referenced in my paper. There was this recent newspaper paper, I think, that showed.
Sorry, can't hear again.
Thank you. There were some recent papers, Elvis Stridham, they're showing action prediction errors, which really map onto our teaching signal for the habit process. That was in rodents. And this model also shared not just the logic part, but the behavior. But there's also a whole, completely separate, habit literature that is actually really difficult to translate to humans. Actually, studying habits in humans has been really, really tough. It was, I kind of accidentally landed on habits in this study, and so I'm not completely sure that that's what this is. And so we actually, I suddenly went to try to test that better. But yeah, I mean, to answer your question, studying habits in rodents is very easy, and so we know that exists out there. Studying habits in humans is really hard. I think that's because also human in a lab use of control choices, and it's really hard to get them to like
Instinctively choose.
yeah. And so that's why I'm a bit hopeful here, because I think it's happening naturally.
You said in your introductory example that cognition is very flexible but also buggy.
Yeah.
But that the bugs is what it allows it to be flexible.
Yeah. What allows it to be efficient, I guess.
Efficient.
Yeah. Right. So the way of saying it here is
So is buggy here means like, you just
suboptimal.
suboptimal,
Yeah,
I see. Okay.
right. So this age can't learner policy, this working memory is, when I took working memory to machine learners or AI people, I'm like, oh yeah, we have working memory, it's fine, RNNs, blah, blah, blah. And I'm like, no, you don't, like a core feature of working memory is capacity limitation, and your RNA is like and you're just assuming that's a bug. You're just assuming that if I have more, capacity, it can only be better. But possibly it's a feature, and I actually think it's maybe a feature. Or it's a bug that makes you more efficient in some way. There's like a trade-off, right? Yeah. So here the idea more efficient is essentially have this process that is efficient in the sense of only having capacity 3, right? It's not like you're crazy, 32,000 kind of LLM. And it's letting you very flexible in learning super fast, but only this other process that's dumb, but very simple to implement, right? It doesn't need to like have 3-factor learning rule. It doesn't need to have, value estimation or anything. It just needs to say like, I did this something, and it's, so in that sense, you can build it as much more simple, more efficient. So I'm not showing evidence for that, I agree. And then you put them together and doing great. They're like kind of covering both of your bases. They're covering, letting you run in the case, and they're letting you run in the hard case. And it's buggy in the sense that, yeah, you're making some weird things, right? You're not paying enough attention to your errors. But it is right. In the end, you're getting it right. It's slightly slower. This is very speculative, right? Like, obviously, I have no, proof for any of this, right?
This is just late into the meeting. We're allowed to speak.
Sorry.
So I think one point you mentioned is about it may not be a bug, but a feature. I think that's a very important point to linger on. Like you're saying that by virtue of having a finite number of neurons or finite working memory, we are forced to maybe abstract away and focus on the most important or salient features. So I think that's the biggest distinction between humans, one of the biggest, and LLMs, which is just concatenate everything in there. So.
And I think it has the flavor of attention is all you need kind of idea. Like, like you get better once you can on a few aspects of problem matter.
Yeah.
And you have too many things, essentially the conventionality and the overlapping. There was one paper showing something like this years ago. It seems super convincing. It was just computational. You know, my dream is to show something like this experience. It's very, very hard. So yeah, we'll get there. But I think it's, I guess, to me, it's a working hypothesis. I guess I think it has some odds of. Yeah.
Sense to me. So there are no more questions. I'm gonna stop recording so we can actually have the final Q&A. Any more questions?